بسم الله الرحمن الرحيم، والصلاة والسلام على أشرف خلق الله المرسلين سيدنا محمد وعلى آله وصحبه وسلم. رأينا في الفيديو السابق التريك الجميل العجيب الذي يعني توصلنا إليه، حيث ربطنا المعادلة فوق الدالة الأسية وعدم التكافؤ بين اللاجرانج والهاملتونيان، ربطناهما بتكون الكتل. توصلنا لمعادلة في غاية الجمال. تعالوا نشوفها. هذه هي المعادلة التي توصلنا إليها، معادلة الهاملتونيان. H يساوي B ناقص C دالة في Q كل تربيع على 2M زائد V of Q. الغريبة في هذه المعادلة أنا تذكرت أن ديراك استخدمها عندما ناقش creation and annihilation operators بالنسبة له. يعني ديراك استخدم هذه المعادلة من أجل أن يحسب الاوبريتورز للكرييشن والانهيليشن، واستخدمها بطريقة عجيبة جدا جدا. طبعا هذه المعادلة هي الهاملتونيان، ويمكن أن نجعلها معادلة لشرودنجر بطريقة جميلة جدا وعادية، وهو ليس فقط كذلك، وإنما يمكن نجعلها طريقة للهاملتونيان على طريقة ديراك اللي هي النسبوية، وبطريقة بسيطة جدا. أنا طبعا تناقشتها وتحدثت عنها في أحد السلسلتين، الشيطان يقبح في التفاصيل أو الملاك يقبح في التفاصيل. في أحد هذه السلاسل أنا مرت علي. فديراك فعل ماذا؟ ديراك فعل أن اعتبر هذه معادلة شرودنجر، فهذا الجذر التربيعي قسمها على 2 حدين مضروبين في بعض، اللي هو بي ناقص سي كيو بي ناقص سي كيو على ام على جذر ام مضروبة في بي زائد سي كيو على جذر ام. طيب هذه هي هذه الطريقة تعطينا معادلة مربع كامل، لكن هناك في كروس تيرنز. الكروس تيرنز ديراك وضع فرضية، هي أن جعل الحدود أو البري فاكتور لهذه التيرمز ألفا وبيتا، وخطة كونديشنز اللي هو إذا كان ألفا مضروبة في بيتا تدينا 0، إذا كان بيتا تربيع تدينا 1، إذا كان ألفا تربيع تدينا 1، وبالتالي يتخلص من الكروس تيرم عن طريق ألفا في بيتا، لأنه الكروس تيرم يعتبر ألفا في بيتا. فبالتالي وضع المعادلات هي الجاما، الحدود الجاما، وطبعا الجاما أيضا بدلالة ألفا وبيتا، لا أتذكر كيف وضعها. وأيضا وضع معادلة نسبوية. فبهذه الآلية وضع ديراك معادلة جميلة جدا وأنيقة جدا جدا بهذه الآلية، وهذه فعلا تعبر عن معادلة شرودنجر، لكن في الوضع الانتراكشن، الوضع التفاعلي، بحيث أن البي ناقص السي كيو. حتى أنا ناقشت في هذا الموضوع وذكرت أن البي تنقص، لأن نحن نتكلم عن فضاء تفاعلي، بحيث أن البي هي مشتقة السرعة أو عبارة عن السرعة مضروبة في الكتلة، والكتلة هي المشتقة المسافة. وعندنا في الفضاء الكثيف عندنا الفلوريت إز هاي في الفضاء الكثيف، وبالتالي يجب على البي في الفضاء الكثيف أن نطرح منها حتى يعطينا الفضاء القليل. بعد ما نحول البي إلى مشتقة، يعني البي عبارة عن بارشل على بارشل إكس. هكذا أنا أتذكر هكذا ناقشته مع معادلة الديراك، وكنت يعني مبسوط جدا جدا أنني توصلت لهذا الاكتشاف الجميل. لم أتوقع أننا نجد هذه المعادلة أيضا في هذه السلسلة. يبدو أننا موعودون يعني بسلسلة جميلة جدا. هذه السلسلة الجديدة موعودون بمعلومات جميلة جدا جدا. طيب تعالوا نبدأ إن شاء الله في الحلقة الثانية من السلسلة.
So let's begin. Continuing our path integral discussion. Here I again show one of the main results of this morning, namely the general path integral, which describes the following: a matrix element between a Heisenberg state defined at some initial time Ti and another Heisenberg state at some final time Tf, and in between there is a time-ordered product of operators, which in this case should depend on the Q's and P's, the operators. And this general matrix element is given as a path integral over the paths of Q and the paths of P. And here we just have the classical expressions of the corresponding operators with number-valued arguments. And here the exponent is this object, which looks like the Lagrangian but isn't a Lagrangian because the P and Q's and Q dots are still independent variables. Now let us go on. We have discussed the transition from the Hamiltonian to the Lagrangian picture, and it isn't a Lagrangian because the P and Q's and Q dots are still independent variables. Now let us go on. We have discussed the transition from the Hamiltonian to the Lagrangian picture, and I gave you already a semi-simple case which is not completely obvious where the Legendre transformation in the path integral works. And now we want to discuss even more general cases. So let me immediately jump right in. What happens if the Hamiltonian contains terms which are quadratic in the P's, like we have assumed this morning, but the coefficient is now not only a matrix, but it is a matrix which depends on the Q's. A matrix which depends on the Q variables, such that the coefficient of the P's in the Hamiltonian is a more complicated function. And then there might be some other terms. If that happens, you can still do the Gaussian integral, but the prefactor is now containing, this normalization prefactor is now containing the determinant of the prefactor matrix, but the prefactor matrix now depends on Q. Therefore, the determinant which appears by doing the integral over P will be a function of Q, therefore a complicated additional piece in the final result. A piece in the final result which will not be of the form e to the I times the action, but an additional factor which is just the functional determinant of the matrix A, which is a functional of Q. Therefore, that provides an example where the path integral will not have the form integral over Q times e to the I times the action. It's just a counterexample. So here the path integral will contain the functional determinant of this matrix A of Q to the power minus 1/2, which is a non-trivial dependence on the Q's, and therefore the final result would be a path integral with a structure like this: dq of t times some other factors, maybe times this determinant of the matrix A of q to the power minus 1/2 times e to the I times integral of the Lagrangian. That is the least that will happen in such a case. And so that provides an example where the general thing that you might always imagine is not correct. So here it's a more complicated situation, and there are some quantum field theories which have such a behavior, for example effective theories, and in those cases then simply the path integral looks like this. Another case which we should discuss is in the case of constraints. You know, this type of constraints in the Lagrangian and Hamiltonian formalism, where the Legendre transformation is also non-trivial, which we have.
طبعا سنناقش نفس ما ناقشناه في الحلقة السابقة وفي بداية هذا الفيديو. طبعا هذه بالنسبة لي مفاجأة، لأن كما قلت أنني لم أمسح هذا الفيديو مسحة، يعني لم أراجعه أو لم أقرأ، يعني أشاهده كبداية لتسجيل هذه السلسلة. فأنا أول مرة أمر عليه هذه السلسلة، أول مرة أمر عليها، لهذا يعني تفاجأت بهذا الأمر، أنه سيناقش ما ناقشناه في الحلقة السابقة، ما ناقشناه في بداية السلسلة عن الكونسترين. طبعا هو هذه بالنسبة لهذه السلسلة هو طبعا سمستر جديد، وهو فعلا سأل الطلاب في الفيديو السابق أنه من حضر السمستر الفات معه، فالظاهر أنه لم يجيب أحد، فبالتالي يضطر لمراجعة الكونسترينز، محاضرات الكونسترينز على ما أظن سيراجعها الآن أو سيتقدم فيها للأمام. هو طبعا أضفى فيها يعني شرح جميل جدا جدا، يعني وقع في العقل ووقع في النفس، يعني حتى شعورنا يعني اختلجت في هذا الشرح الجميل. لماذا؟ لأنها فهمتنا ميكانيك الكم، واستطعت أن أربط نظرية مباشرة بميكانيك الكم من خلال هذا الشرح. فشرح جميل جدا جدا كان، وكانت بالنسبة لي نقطة مفصلية حقيقة بين الانتراكشنز وميكانيك الكم والكيو اف تي وبين نظريتي، يعني مرحلة مفصلية، أو كما يقال أنها الكي وورد بالنسبة لفهم العلاقة بين نظرية وميكانيك الكم، وبسببها عملت هذا الكتاب الحلقة 54. نعم. طيب تعالوا نواصل.
Discussed in quantum field theory 1. And as you already know from quantum field theory 1, the case of constraints is very important in quantum field theory. It appears in very many very relevant field theories already in the Dirac theory, but also in the case of vector bosons, both with masses and without masses. Therefore, constraints should be dealt with, and we should understand how to use them. And so that is the main point I want to discuss now. And that is the general result I want to give you. I will now spell out a few conditions under which the usual thing with just the action in the exponent is correct, and the list is long, and we will then provide examples, and you will discover that those examples are exactly the relevant ones. So assume the following case. Namely, we allow second-class constraints which are the simpler kind of constraints. You remember, first-class constraints are gauge invariances. Second-class constraints are those ones where you can eliminate something by using the equations of motion. And so this is what we allow. then we have variables in our theory which we give typical names, let's say Q1 or Qi in general, Pi. Those variables are unconstrained. And we have an additional set of variables, let's call them Qbi. B always for me stands for an auxiliary field which is constrained. Qbi and Pbi of some number, they are constrained. Then we assume the following form of the Lagrangian. The Lagrangian should have a first part which I call L0, which contains only the unconstrained variables Q and Q dot. And this Lagrangian should be as in the previous section, so that we already know that for this one alone the transition in the path integral works. And then comes the dependence on the extra constrained variables, and I assume the following form, which is in all relevant cases true. Namely, 1/2 times a matrix small aij times qbi qbj. So a quadratic form in the constrained position variables plus qbi times the following, another matrix bij times qj dot plus ci of q. Okay, and maybe later I will abbreviate this whole thing as fi of q and q dot. So what do we have here? We have the following. The Lagrangian does not contain qb dot. So these variables, which I call constrained variables, their time derivative does not appear. That is why they are constrained. But the QBs on their own, they appear, and they appear only in a quadratic form. Here, the worst that can appear is a quadratic thing, which has a constant coefficient, and then they appear linearly, and the linear term contains the velocities of the normal variables and something like an arbitrary function of the normal variables. Okay, that is the structure, and you will see that in all our relevant examples, this structure is fulfilled. And that is the structure we can deal with, and I can tell you immediately that for this structure, the transition to the Lagrangian in the path integral works completely. So let's write down some facts. So the derivative dl by dqbi dot, that would be the definition of the momentum, right? The canonical momentum. But this derivative is 0, and that means there is no canonical momentum for those QB variables. That is the point, and that is what we mean by constraint. That is a constraint, and then the dl by dqb without dot, that is not 0, but that is this aij qj plus fi of q and q dot. And the equation of motion for those qb variables, the equation of motion would be that this is equal to the time derivative of that. The time derivative of that is 0. Therefore, the equation of motion tells us that this should be 0 as well. So the equation of motion tells us that this object here should be 0. And now we assume.
طيب قبل أن نستمر تعالوا نشوف هي بس لحظة.
That the matrix here is invertible. This matrix here should be invertible. Otherwise, the construction also doesn't make sense. And then we can solve the equation of motion for the QB. We can solve the equation of motion for the QBs, namely QBJ or QBI would be this matrix small a to the minus 1 ij minus times fj of q in q dot.
طيب قبل أن نستمر هو وضع تو كونسترينت. الأول أن المشتقة للاجران بالنسبة لكيو بي دوت اللي هي طبعا تعبر عن السرعة يساوي بي يساوي 0، وهذا تعني عن المشتقات الزمنية اعتماد على المشتقات الزمنية للكانونيكال مومنتوم يساوي 0. وثم بعد ذلك أجرى اشتقاق بالنسبة لكيو بي اي وجعل تساوي 0، وهذه هي الإيكويشن اوف موشن لأنها تحتوي على كيو دوت. كيو دوت يعني مشتقات زمنية. أي معادلة تحتوي على مشتقات زمنية مشتقات مكانية هي عبارة عن معادلة حركة موشن إيكويشن اوف موشن، خصوصا إذا كانت تساوي 0. إذا كانت لا تساوي 0 فهي معادلة حركة، لكنها حركة إما تناقصية أو تزاويدية. طيب جميل. طبعا الشرط الذي يوضح هنا طبعا هذه كلاس 2. فكلاس 2 الشرط هو أن المشتقة الثانية لابد أن تكون تساوي المشتقة الأولى وتكون يساوي 0. في هذه المعادلة لابد المشتقة الثانية تكون مشتقة يعني المعادلة التي تحت يساوي المعادلة التي فوق يساوي 0. إذا جاءت لا تساوي 0 فهنا يعني أن ما يحتمل هذه عدم المساواة هي الكتلة. لهذا نجد أن معادلة الحركة الإيكويشن اوف موشن ظهرت في الاشتقاق الثاني في المعادلة الثانية، وأيضا سواها ب0، وبالتالي تعبر عن معادلة الحركة. طيب جميل. هذه تعبر عن معادلة الحركة لأنها إذا طرحت منها الاشتقاق الفوق المعادلة الأعلى لا تساوي 0، وهذا شرط. لكن أين الكتلة هنا؟ لماذا لم تظهر الكتلة هنا؟ الكتلة ستظهر داخل معادلة الحركة اللي هي في الإف تحديدا، في الإف كيو نوت. هذه الإف كيو نوت. هذا السي التي هي دالة في الكيو تعتبر معادلة الحركة، لأنه السي في الكيو هي تعبر عن الكيو تعبر عن الجهد دائما مع الكتلة. فهذه مع هذه الاف تعبر عن داخلها الكتلة. طيب إذا هذه معادلة حركة داخلها الكتلة. كيف لنا أن نحسب أو من هذه المعادلة كيف لنا أن نتبين الكتلة؟ لاحظوا كلامي هذا مهم جدا. أنا ذكرت في الفيديو السابق أن هناك الشرط أن المعادلة التحت يجب أن تكون تساوي المعادلة الفوق. إذا لم تساوي المعادلة الفوق فإنها تعبر عن الكتلة، وهذا صحيح، هي تعبر عن معادلة حركة داخلها الكتلة. لكن نحن ما لا نريد معادلة حركة داخلها الكتلة، نحن نريد الكتلة مباشرة بحيث نستطيع تتبعها من بداية التفاعل حتى نهاية التفاعل. كيف نفعل ذلك؟ فقط أننا نجري اشتقاق للمعادلة الثانية. طبعا هي تساوي 0، أجري اشتقاق عليها. الحد الأول إذا كانت هذه المعادلة ثابتة يعني لا يمكن اشتقاقها، في الحد الأول يساوي 0، والحد الثاني الذي يحتوي على الكتلة يجب أن يساوي 0. لكن نحن نرى أن الحد الثاني من هنا، الحد الثاني عبارة عن حدين، عبارة عن هذه المصفوفة مضروبة في كيو نوت، والسي مضروبة في كيو، وكيو نوت يمكن اشتقاقها مرة أخرى، يمكن اشتقاقها لا تعبر عن السرعة، إذا اشتقت تعبر عن المسافة، وبالتالي تعطينا هذه الاشتقاق تعطينا عجلة زائد كتلة، أو عجلة زائد معدل تغير الكتلة. معدل تغير الكتلة هذه ما يعطينا نظرية بالضبط عن السيمتري اللي بينكسر، الذي ينكسر داخل الكتلة ويعطينا كتل، أو ينكسر داخل الانتراكشن ويعطينا كتل غير متساوية. هذا بالضبط. يعني يمكن نعتبر الإيكويشن أوف موشن اللي هو المعادلة الثانية، نعتبرها هذه المعادلة الثانية يمكن أن نعتبرها نيذر ثيوري، نيذر كرنت اللي هو تيار نيذر، والتيار مفترض يكون متساوي ومستقر، بحيث أنه مشتقة له تساوي زيرو، وإذا كانت المشتقة له لا تساوي زيرو فهذا يعطينا مباشرة التغير في الكتلة. هذا ما تقوله نظريتي، وربما هذا ما يتطرق عليه هو أو ربما لا، لكن هذا ما تقول عليه نظريتي. إذا كنت تريد أن تتابع تغير الكتل في التفاعل وتطورها، أحسب تيار نيذر واعتبره ليس مستقرا، وحاول أجري الاشتقاق عليه مباشرة، سيعطيك التغير في الكتل والتغير في السرعة، وأيضا يعطيك numbers of masses اللي هو عدد الكتل. 3 أشياء. ربما يعطيك السبين أيضا، التغير في السبين، لكنه عبارة عن تغير كلها تغير في السرعة يعني عجلة، تغير في الكتلة يعني كسر التناظر، تغير في السبين يعني شيء آخر، وهكذا كلها تغير. تيار نيذر يخبرنا بالتغيرات التي يحصل للكتلة، وأيضا التغير في الكتلة يمكن تتبعه بحيث أن تجري الاشتقاق بدلا من تجريه للزمن ممكن تجريه للمسافة. إذا جريت اشتقاق للمسافة فهذا يعطيك ماذا؟ السرعة ستكون تساوي زيرو، لأن السرعة عبارة عن مسافة بالنسبة للزمن. إذا اشتققت للزمن تعطيك عجلة، لكن إذا اشتققت للمسافة مفترض تعطيك زيرو. الكتلة ستعطيك تغير في الكتلة. إذا السرعة لم تعطيك زيرو فإنها ممكن تساوي الحدين مع بعض وتعطيك تغير في الكتلة. نعم، تعطيك تغير في الكتلة، وهذه ليست لها علاقة بالعجلة، وإنما لها علاقة بأن السرعة تتغير مع المسافة، تغير السرعة مع المسافة وليس مع الزمن. وهناك فرق أن السرعة تتغير مع المسافة ومع الزمن. مثل في كتاب الحلقة 54 توصلت أن المجال المغناطيسي الذي يتغير مع الزمن يعطيك مجال كهربائي طبعا، لكن أنا جعلت المجال المغناطيسي يتغير أيضا مع المسافة، وهذا ما يعطاني التغير في الكتلة، يعطاني تغير مجال مغناطيسي يتغير مع المسافة. يعني المجال المغناطيسي يتغير في 2 مع الزمن ومع المسافة، إذا له اشتقاق من الدرجة الثانية، فهذا يعطينا التغير في الكتلة مباشرة. فهذا أمر جميل وعجيب.
So this is the solution of the equation of motion. And this is another constraint. So on the level of phase space, the whole theory is only defined on the submanifold of the phase space where this equation and that equation is valid. Outside of that submanifold, the phase space cannot be reached in this theory. So that is what we call a constraint. And the statement is the following. Under this condition, the correct path integral is the following, namely QF TF, then time ordered product of some operators in the same sense as before. If they only depend on the Q's, not the P's, Q's, and they might even depend on the QB's, which are constrained, but not on the P's, QI, TI. That is given by what you expect, namely just the path integral over Q, including the path integral over the constraint variables QB, just over all variables which exist, then all these operators OM of Q, TM, QB, TM, and then the exponent e to the I times integral of the Lagrangian LDT. So that is the most naive path integral that you can think of. You just ignore everything about all difficulties, forget about constraints, forget about variables, just take the Lagrangian as it stands, take all the variables which it depends on, all position variables, integrate over them, and that gives the correct result. And this can be proven on exactly this general level, but I'm not going to prove it. Let me just write it down. We will give the proof for specific examples. Why? Because then you will see which examples this corresponds to, and you will see exactly the application, and you see why exactly this structure is important and also why it is sufficient. We will discuss the exact notation, which is the field theory notation, where this will be important, instead of using an abstract notation which will never be used again. And the structure of the proof is of course exactly the same, regardless whether you work in an example or in the general case. That's the point. Very good. Okay, therefore, let's go to the examples. And in case you have forgotten what constraints are and so on, then this will also probably become clear again from looking at the examples. So I will go through 3 examples, and let's put it here, 1.5 relevant quantum field theory examples. And let me already point out what we will do now is basically an answer to the discussion at the end of our section, what was it, 338 in Quantum Field Theory 1 from last semester. Because there we discussed the derivation of Feynman rules, and I gave you a long list of very general Feynman rules, and we derived them at an example. Namely, we derived them for QED, and then I said the same Feynman rules and the same recipe is always true. But I also told you that the derivation is sometimes extremely awkward because there are certain problems in the derivation, and I told you that in Quantum Field Theory 2 we will solve those problems, and that is now. Okay? So therefore, please have a look once again at those remarks over there and see the derivation of Feynman rules in the canonical operator framework, and then we will compare it to here. So we will actually not immediately derive the Feynman rules, but what we will derive now is the path integral, where you will already sense why and how the problems that we encountered there can be solved. And in the next lecture we will also look at the Feynman rule derivation from the path integral, and then it will turn out to obviously avoid all those problems and directly lead to the rules which I have already stated there. The first example is a scalar field with derivative couplings. Scalar field with derivative couplings. Let me write the Lagrangian and then clean the blackboard. So the Lagrangian would be this, 1/2 d mu phi minus m square over 2 phi square minus j mu d mu phi minus the potential v of phi. And this term here is the special term which is now new and which contains derivative interactions. So this j is basically just an abbreviation for some interaction of d mu phi with some other fields. We don't specify which fields these are. It might be a product of some other fields, but we don't care about that. We only care about the phi dependence. And here there is a derivative of phi in the interaction term. And that is something for which I already gave you the recipe to read of the Feynman rules, but I told you that the derivation is more complicated. Okay, and so let us now look at this. So let's look at this and really go through the canonical procedure, which is the procedure that we have trained ourselves to do in the last semester. So for those of you who were not there, okay, you can still follow, I hope, canonical procedure. But for those ones who were in the last semester, this is now Pavlov's reflex, because we did it so many times for so many different cases, but not for this one. Okay, so what happens? We need to first look at the conjugate canonical momentum pi, which is the derivative of the Lagrangian with respect to phi dot. The derivative with respect to phi dot. So where is phi dot? Phi dot appears here, phi dot square from the d0 derivative. So the derivative gives us phi dot. Here there is no phi dot, but here there is another phi dot, namely minus j0. So phi dot, for those who forgot, is the same as this and also the same as this, because we use a metric where for the time component the upper and lower index is the same. Okay, so that is our conjugate momentum. So we can solve that for phi dot. Phi dot is then pi plus j0. And in the usual case where we have a free scalar field like this one, we would just have phi dot equal pi. And now we have phi dot equal pi plus this additional term. Then our Hamiltonian is a d3x integral over some Hamiltonian density, and the Hamiltonian density is given now by the Legendre transformation, namely pi times phi dot minus L. And okay, so we can plug in everything, pi, and we have to eliminate, of course, phi dot by saying phi dot is equal to pi plus j0. That is part of the definition of the Hamiltonian. So let's plug it in. Phi dot is replaced by that. So we get here one term is pi square. And here from the Lagrangian we also have 1/2 phi dot square. That also gives us 1/2 pi square. 1 pi square minus 1/2 pi square is 1/2 pi square. And then from here we have the spatial derivative terms. Here they come with a minus because of the metric, and in minus L they come with a plus. So plus 1/2 gradient phi square. Then we have here plus m square over 2 times phi square, and plus the potential v of phi. And here now I've really calculated just all the terms without the current j. And now let's care about all the terms involving the current J. So where are those terms? So one term is here from pi times phi dot. Phi dot contains J0, so we get here pi times J0. Here from this 1/2 times that thing, here we get a square terms, phi dot square, we get pi times J, 2 times pi times J cancels the 1/2. So this term drops out, I would say. And anything else? Yeah, here, J0 times phi dot once again. So from here we then get finally once more J0 times pi, so one term plus J0 times pi remains. Then what else do we have? We have from here the spatial components plus Ji times di phi. And then from here we had pi dot square, which gives us one term J0 square, so plus minus 1/2 J0 square. And that's it, I would say. Good. So, and now we can look at the terms a little bit. So this first part here, this would be the free Hamiltonian of the free scalar theory that we discussed in quantum field theory 1, which has absolutely no interactions. And so we discussed that and did canonical quantization of exactly this expression. This comes from ordinary interactions with the potential, and that is the new term coming from the derivative interactions. And all of it is the Hamiltonian density. And so now you see the problem which I already mentioned last semester, namely here there is something which is not Lorentz covariant. We simply have the zero component J0 square in the Hamiltonian, just like that. So this is not Lorentz covariant. Okay, none of the terms are Lorentz covariant, okay, but this is particularly non-covariant, is even less covariant than all the other terms in some sense. So it's a square term in J, but just involving the J0 component. And so then the other thing, in the derivation of perturbation theory, we would encounter then interaction picture and so on, and then at some point there is an interaction Hamiltonian, which is everything except for the free Hamiltonian. So everything except for this bracket. And we simply said usually this is equal to minus the interaction Lagrangian density. And that was usually true. But here it's not true, because the interaction Lagrangian density is just this here. Very simple and very Lorentz invariant. But the interaction Hamiltonian is totally non-Lorentz covariant and is definitely not equal to minus L int. So this was also a remark that I made, that this relationship that we always used is sometimes wrong. Here it is wrong. So that is not true. Here we have something non-Lorentz covariant. And in the operator formalism, all of this is what we would need to use. We would have to use exactly this. We would not be allowed to use directly L int. We would need to use this Hamiltonian density in order to derive Feynman rules. Then we would have, of course, not Lorentz invariant Feynman rules, special vertices involving just this, and so on. So that is what we would need to use in the operator formalism. But now let's look at the path integral. So let's look at some final state at Tf and some time ordered product of some operators, O1, of phi, and so on, Om. of phi some initial state. We know that the correct path integral is really the one with the Hamiltonian, and where we integrate over position and momentum variables. So here we integrate over the field and the conjugate momentum field. So that is clearly correct, and then we have an exponential of the integral over the Hamiltonian minus this other thing. So we have this pi phi dot minus h integrated over d4x. This is our correct path integral, and we know it's correct. We have derived it simply under the condition that there is a Hamiltonian framework. We have a Hamiltonian framework, therefore we know that this is correct. And this is also not Lorentz covariant because it has exactly the same problem inherited from the Hamiltonian framework. So here we have our weird looking Hamiltonian density. But now we can use the transition of the path integral from Hamiltonian to Lagrangian, and then all the problems will dissolve. So, right, let's call this again e to the I times sigma. Sigma is basically the exponent. Then we see sigma is as the form basically something involving pi square plus something involving pi plus terms which are not pi dependent, and the coefficient of pi square is an invertible constant which does not depend on the fields, is 1/2. So therefore our conditions for doing the Gaussian integral are satisfied. We can do the Gaussian integral. It is trivial. It will lead to a normalization prefactor which depends on nothing. Therefore we can ignore the normalization prefactor, and then the Gaussian integral will simply have the effect, as we discussed, to replace this object by itself where we evaluate it at a stationary point. And that then corresponds to the Legendre transformation. So here this is constant and invertible. So we can integrate over the pi, and the result will be e to the I sigma, where we must replace pi by pi star, where pi star is defined such that the variational derivative here of sigma with respect to pi at pi equal pi star vanishes. And this condition here, the stationary point condition, is of course nothing but saying that phi dot is equal to the derivative of h with respect to pi, which is the Legendre transformation. Therefore, this result here at this stationary point of pi is nothing but e to the I times the integral of the Lagrangian L d4x. And that is now the original full Lagrangian with all its details, with all its terms, but in particular the Lorentz invariant form of the Lagrangian. So here in this small sequence of steps, all the known Lorentz invariant stuff has completely dropped out. And we can simply say, let's call this star. This is our original path integral, and to have a nice result at the end, this star is now really equal to path integral over only the fields d phi of x, then all the operators, and then e to the I times integral over L d4x. As simple as that. And here we have the fully Lorentz invariant Lagrangian density, which originally defined our theory. So this is the outcome of that analysis. So this
طبعا بهذه الطريقة ما دام عملها لاجرانج انفاريانت، يعني انفاريانت تحت لورنس ترانسفورميشن، هذا يجعل ماذا؟ هذا ما جعل ميكانيكال كم لا تخبرنا بالكتلة. الغرض من أننا نخبر بالكتلة هو أن نجعل لاجرانج نون انفاريانت، وبالتالي الباث انتجرال سيخبرنا الايكويشن اوف موشن صحيح، لكن هو الايكويشن اوف موشن للكتلة من مكان إلى مكان انتقل، يعني بالكامل الكتلة بالكامل تتحرك من مكان إلى مكان، وهذا يظهر في شكل تيار. هذا التيار مجموع الكتل فيه موحدة، لكن الكتل الداخله ليست موحدة، وبالتالي الباث انتجرال لن يخبرنا بالتغيرات التي حصلت داخل الكتل، لا يخبرنا، لكن يخبرنا بانتقال الكتل. نعم، أو مثلا خلق الكتل، يخبرنا أنها تم خلق كتل، والكتل التي تم خلقها تجدونها في الزوايا الحتة الفلانية المكان الفلاني، وهكذا. تحول الديتكتور إلى المكان الفلاني تجد النتيجة، تحول الديتكتور المكان الفلاني تجد النتيجة، ولكن تجدها في شكل تيار، تجدها في شكل تيار من الكتل، لكن لا تستطيع أن تجدها تجدها كتل يعني ربما تجدها كتل متنوعة، أو ربما تجدها كتلة واحدة، يعني أي تايب وان تايب من الكتل، لكن في النهاية لا تستطيع أن تحسب عدد هذه الكتل، لأن أنت في النهاية جعلت المعادلة لورنس انفاريانت، لكن إذا جعلتها لورنس ديبندنت يعني تتغير تحت لورنس، هنا يمكنك أن تحسب الكتل، ويمكنك أن تحسب العدد، ويمكنك أن تحسب كل شيء. نعم.
So this is the first example, which is already a non-trivial example, where the power and the magic of the path integral becomes visible, and its great advantage over the canonical formalism becomes obvious. So the next step could then be to read off Feynman rules from here. We will learn how to do that in the next lecture, and then those Feynman rules will immediately be automatically known. Any questions? Yep. Okay, here we have this path integral with the specific initial and final states at specific times which are not infinite, and so therefore the boundary condition of the path integral is that the field configurations at those times match the fields which are specified by the initial and final state. So these are boundary conditions of the field at finite times. And here the integral goes from Ti to Tf, not from minus infinity to plus infinity. Of course, in the spatial sense, for spatial x, the integral goes to infinity. And then, of course, it depends on the boundary conditions that you have put here for those initial and final states. I mean, the integral is proved to be the same as the original matrix element. And if the original matrix element is finite, then this integral will also be finite. Sometimes, however, of course, matrix elements between non-normalizable states in quantum mechanics might be a delta function and so on, and then you cannot expect this to converge as well. But if you choose here a matrix element between states which are normalizable and so on, such that the original left-hand side of the equation is finite, then the integral is guaranteed to be finite as well. Okay, because here sigma is an integral over all field configurations, and here I would use a functional derivative with respect to one particular point pi at some x, specifically at some value of x. That should be 0. That is the same kind of functional derivative as you are using in classical mechanics to minimize the action. There you have a function of time. Here we have a function of time and space, but it's the same idea. That was already an important example, which appears in actual physics applications, but the example did not yet contain constraints, but nevertheless it was already interesting to look at. And maybe let me give you a reference so you can find more about this example also in Weinberg's book, section 7.5 and section 9.3. So the discussion of this is spread over exactly those two sections. Now let us the massive vector field. The Lagrangian density is minus 1 over 4 f mu nu f mu nu plus m square over 2 a mu minus j mu a mu. So this is the normal field strength tensor, which is an abbreviation for this antisymmetric derivative. This is a mass term for a vector field, and the combination of the two terms is something that we quantized in quantum field theory 1, with the result of finding a massive spin 1 field and a massive spin 1 particle in the spectrum of the theory. And the interesting detail was that we have 4 components of our field A mu, which runs from 0 to 3, 4 components. Therefore 4 degrees of freedom on the level of field variables, but the physical spin 1 particle has only 3 spin degrees of freedom, spin +1, -1 and 0. Therefore there is a mismatch of the number of field variables and the number of particle degrees of freedom, and the mismatch is taken into account by the fact that this Lagrangian is one which has constraints. It has one constraint, and this constraint eliminates essentially 1 degree of freedom, and we discussed all of that in our discussion in quantum field theory 1. Now we look at the Lagrangian of that massive vector field and add an interaction. This is an interaction term, again in some generic form, where I just put in some j. We do not ask what is this j in detail. It is, at least it shouldn't contain the a mu, but otherwise it is whatever it is, and it corresponds to some interaction which we would now like to take into account in order to understand how we can derive Feynman rules for such a field theory with interactions. So the equation of motion corresponding to that Lagrangian, if you do Euler-Lagrange as usual, gives you d mu f mu nu from the field strength tensor plus m square a nu, now minus j nu. So this thing here was the equation of motion that we quantized, and that is now an additional term. So let us go through the canonical procedure again. And of course we did that, except for with the j, we did it in quantum field theory 1. So we pay particular attention to the j-dependent terms, but let's go through the steps. First, the definition of the conjugate momenta, pi mu, is given by the derivative of the Lagrangian density with respect to a dot mu. with upper and lower indices like that. And then, so the question is, where appears a dot mu, or the zero derivative of a mu? So it appears within the field strength tensor in f mu nu f mu nu. So one term here from this, the 1/4 cancels, and we get just minus f0 mu from that derivative here. Then the second term does not contain it, and the third term okay, that's it. So there is no other term. So that is just a canonical momentum. Okay, but let's look at it in some detail. So actually, what happens for mu equals 0? So what is the canonical momentum for the A0 field? It is 0, because the field strength tensor is antisymmetric. F0, 0 vanishes. So for the field A0, we get the canonical momentum vanishes. And that is a constraint. That is what we call a constraint. So there is no, the phase space of this theory does not lead to points where pi 0 is unequal to 0. So the phase space is not a full 8-dimensional space, but only a 6-dimensional submanifold is filled with valid points. And so here in the other case, we can get rid of the minus and write it as plus fi0, where mu is equal to I. That is unconstrained. Then, is this a first class or a second class constraint? Who knows it? Mr. Schäuble. Yeah. In order for it to be second class, we need to find a second constraint with which together this forms a pair. And so let us find this second constraint. So let's look at the equation of motion. Here is the equation of motion in general, but let's look specifically at the equation of motion for our constrained field A0. What is the equation of motion for the constrained field m square A0? Is equal to J0 minus d mu f mu nu, and so here f0. So we only get spatial indices here because the f0, 0 vanishes. So that's all we have. And then you see that actually this here is the canonical momentum. So we can also write this as J0 minus di times pi I. That is our equation of motion. And this is also a constraint, because it gives a relationship between our field variable and other field variables and canonical momenta without time derivative. Such a thing is also a constraint. So again, you cannot choose initial conditions for the time derivative and so on for this field, but A0 basically is an abbreviation for other phase space variables. Once those phase space variables are fixed, A0 is fixed as well. That is also a constraint. And now that is the thing of second class and first class constraints. Second class constraints are those ones where you can form a pair of two constraints. Here one constraint for A0 and another constraint for pi 0, and the Poisson bracket between the two doesn't vanish. So the Poisson bracket between A0 and pi 0 of course doesn't vanish. So that was the criterion, and so here that criterion is fulfilled. So therefore we have here second class constraints. And if you don't know what we are talking about because you missed the lecture last year, then you can look it up. But the point is simply first class constraint gauge theories. This is not a gauge invariance, but it's a second class constraint. And as you see from the concrete formula, what that simply means is that you can view A0 as an abbreviation of something else, and then you can eliminate. You can just, wherever you see A0, you can now plug in this expression or that expression. It's just an abbreviation, And so you can completely eliminate A0 from the Lagrangian and then go on. That is the simple procedure. Okay, in order to proceed, what we also need is the time derivative. So A dot with index I, A dot with index I, this is here contained here, is equal to di of A0 minus pi I. So this would be a way in the Legendre transformation to eliminate the time derivatives of our field variables. By eliminating them, we encounter our A0, but A0 can then be replaced by whatever it is, using the equation of motion and the constraint. So having all that, we can, let me introduce an abbreviation. Let's call it L constraint. L constraint would be the Lagrangian where we implement everything I said, namely we eliminate A0 by its solution of the equation of motion. So you would eliminate A0 by plugging in this relationship, then A0 doesn't exist anymore. And then, of course, the Lagrangian looks a little bit different, and if you imagine writing it down explicitly, we will not write it down, but it would become quite lengthy. And it also would look completely non-Lorentz invariant, because A0 is then singled out. You replace A0 by this sum, and then, for example, here in the mass term, you would have a mass term for the spatial components, AI. That looks okay. Then you have A0 square. A0 square would be replaced by the square of this, and so then you would encounter such terms in the Lagrangian. And that is the Lagrangian which I call L constraint. And that is the basis of our canonical quantization procedure. So then we, and also that is what we did in quantum field theory 1, except that the J was not there, but everything else was there, and we dealt with it. So then the Hamiltonian density is pi I times A dot I minus the Lagrangian density of this constraint Lagrangian, where the A0 does not appear anymore at all. It's completely eliminated. And so this Hamiltonian density, which we obtain in this way, can be, of course, split into a term which does not contain the J, and a term which contains the J, and the term without J is exactly the one from the last semester, and the term with J is new. So this calculation is maybe a little bit awkward and time consuming and boring, and since it's not covariant, it's exactly the opposite of elegant. Therefore, let's just copy the result from last semester, minus 1/2 pi I plus 1/2 m square times di pi I dj pi j plus 1/4 fij minus m square over 2 ai. That is the term from last semester. And so here, for example, this thing here is exactly nothing but the magnetic field B square. So this contains the magnetic field component, so it's B vector square. Very nice term. This term, or one of the other terms, gives the electric field E square, and there are some other terms. Okay, and now we have some additional terms. So our A0 is changed. Our A0 is changed by the additional term coming from the J. So it's whatever it was before, plus 1/m square times J0. Then our A dot I is also changed. Our A dot I is changed by whatever it was before, plus 1/m square times di J0 from this object here. And finally, our Lagrangian density is whatever it was before, minus J0 A0 minus Ji AI. Okay? And if you take into account all those changes, then I will now simply write down the result that you obtain after plugging in everything. Are you able to plug this in yourself? If not, then I have to teach you how to do it. Is it still running? It's still running. Okay, so let me just copy the result here from my notes. In the end, after a few beautiful, entertaining steps of a calculation, you obtain the following result: J0 di pi I plus 1 over 2 m square J0 square plus Ji AI. Okay, some terms drop out, and in the end you just obtain those three terms. And here you see again this J0 square appears explicitly, which is again completely non-Lorentz invariant as the same J0 square which also appeared in the previous example. And here you have an interaction between J0 and the momenta, here Ji and AI, and so on. And again, of course, if you would now take the sum of the Hamiltonian, so this is the Hamiltonian from before, and that is the free Hamiltonian without interactions. That is the interaction Hamiltonian. Then you can ask again, is the interaction Hamiltonian the same as minus the interaction Lagrangian? The interaction Lagrangian is simply this. This is our interaction Lagrangian. Beautiful, compact, and Lorentz invariant. This is our interaction Hamiltonian, ugly and long and non-Lorentz covariant. So of course this is not the same. It's again one of those examples where this transition is not the same and it is also non-Lorentz covariant. Okay, and however, this would be exactly what is needed in the operator approach. And now, of course, comes to the rescue the path integral. What do we know? We know that, of course, at first we have a canonical formalism with this Hamiltonian, and the Hamiltonian satisfies all the conditions such that we know that the Hamiltonian path integral is definitely correct. So we have a correct, well-defined starting point, which is definitely this one, where we integrate over the canonical variables which exist in our Hamiltonian setup. In the Hamiltonian setup there exist only the spatial components because A0 doesn't exist anymore, it is eliminated, so only AI exists, and the pi i's, they also exist. And then our path integrand, let's say some abbreviated form, simply some operators which might depend on AI, and maybe they also depend on the eliminated A0, which has been replaced by whatever it is according to the equations of motion. And then we have this exponent pi I AI dot minus h d4x. This path integral is definitely correct, and it gives us the usual left-hand side. Point, which is definitely this one. where we integrate over the canonical variables which exist in our Hamiltonian setup. In the Hamiltonian setup there exist only the spatial components because A0 doesn't exist anymore. It is eliminated. So only AI exists, and the pi i's, they also exist. And then our path integrand, let's say some abbreviated form, simply some operators which might depend on AI, and maybe they also depend on the eliminated A0, which has been replaced by whatever it is according to the equations of motion. And then we have this exponent pi I AI dot minus h d4x. This path integral is definitely correct, and it gives us the usual left-hand side, the matrix element that we always had. And now we want to rearrange the path integral and make the transition to the Lagrangian. So in order to make the transition to the Lagrangian, we again integrate over the momentum variables. And therefore we need to ask whether we can again use Gauss integrals. And we can, because the Hamiltonian and the entire exponential here is quadratic in the pi's. The Hamiltonian is quadratic in the pi's. It contains here pi square with prefactor 1/2, which is invertible and independent of the other variables. Here we also contain pi square. The prefactor is here a derivative, which is non-trivial, but it still is not depending on the other fields, so it contains no dynamics. And then there are linear terms in the pi's, but basically the structure is such that we can do Gaussian integration. So Gauss applies, and therefore if we do the integration over this pi I of x, then we have the usual rule, the integral or the integrand becomes just itself evaluated at the stationary point. The integrand becomes the original integrand but evaluated at pi I equal pi I star, where pi I star minimizes this exponent. In other words, AI dot is equal to the derivative of the Hamiltonian with respect to pi I at pi I equal pi I star. So, and this is the definition of the Legendre transformation between the Hamiltonian and the Lagrangian. Therefore, the integrand contains here the Lagrangian in the exponent, but not the original one, but this constrained Lagrangian. This constrained Lagrangian is the one which is connected to our Hamiltonian by Legendre. So from this integration we will obtain this Lagrangian here. So the exponent becomes integral over this constrained Lagrangian integrated over d4x. So this is still not covariant. Okay. So far the path integral has not completely rescued us, but we are not yet done. We can do something else, and we simply try now our hope, because our hope would be the following. Our hope would be that we can use the naive path integral, which you know and love, where we integrate over all a mu's in a Lorentz covariant way, and where we simply have here the original Lagrangian. So let's simply try what happens if we plug in this one. Okay, so we have here the full Lagrangian, without constraints. Here we integrate even over a0, even though this is a constraint variable which doesn't exist in the Hamiltonian framework. And here we have in the operator our a0, which is the integration variable and not the one obtained by solving the equations of motion. So 3 differences. Let's just look at this path integral. What happens if we now evaluate the integral over the 0 component? So let's write this as ai, and then another integral a0, then here the operator and the exponent. Okay. Now let us evaluate the integral over the component a0. So how does the integrand depend on a0? The integrand depends on a0. Here we have the original Lagrangian. The original Lagrangian was of course also quadratic in a0. Therefore, if we integrate over a0, we again get a Gaussian integral, and the result is the same as always, namely the a0 integral is done, and the remaining integrand remains what it is, but with the replacement that a0 is replaced by the stationary point of this, which means that a0 is replaced by its solution to its equation of motion, which is exactly this. Let's write it down. Gauss integral over a0 gets the same effect, namely a0 will become a0 solution of the equation of motion, and therefore the integral will be equal to this here. Also in the operator, a0 is replaced by the stationary point, and here in the exponential we have this constraint Lagrangian integrated over d4x. And then you see that from this starting point here, which is the beautiful fully Lorentz covariant path integral, we get this. And this is exactly the same as what we get from the correct path integral by integrating over the momenta. So in other words, we have proven in this indirect way that the correct path integral is equal to this beautiful path integral, and therefore we have derived our desired equality. Let me write it down. The correct path integral is equal to the following, namely to this. And this is of course completely manifestly Lorentz invariant. All the problems have miraculously disappeared. No constraints visible anymore. Just treat A0 just like all the other fields. Ignore that it is constrained. Just take the original Lagrangian, even though not all variables are dynamical variables, and integrate. That's it. And if you want to know more about this, there is the book by Duncan, which contains this as an exercise, 12.4 exercise, so you can look at this. And again, also Weinberg discusses it in section 7.5 and section 9.3. So Weinberg goes through the same kind of examples as we do here in the same order. Now I wonder whether actually the third example is necessary or whether we should skip it. The third example is even simpler than the second one. Maybe let me first clean the blackboard, and then you can think of whether you like to go through a third example. Maybe I will.
طبعا هذه الإجراءات المعقدة جدا جدا للسبين 1 في النهاية يعني كما رأينا في بدايات السلسلة ستعطينا الكوانتيزيشن وتعطينا يعني الكتل وتعطينا هذه الانتراكشنز التي تحصل للسبين 1 بارتكلز، لكن لا أعتقد أنها يعني تستطيع أن تعطينا الكتل تحديدا. وطبعا هنعرف أن كتل الدبليو زي تتنبأ الكتلة أو تجرى الكتلة، تحسب الكتلة من الاتجار من خلال الديكي للزي يعطينا ميون، وبالتالي هذا الميون موجب وميون سالب، وهذه الميون تقاس ويعطينا الزي مباشرة كتلته. أما الدبليو طبعا يعطينا ميون ويعطينا نيوترينو، ميون ونيوترينو، وتقاس كتلة الميون ومحاولة قياس كتلة النيوترين أو الطاقة عموما، طاقة الميون وطاقة النيوترين، ونحسب الدبليو كتلة الدبليو. طبعا الشحنة تلعب دورا هنا في موضوع الكتل متساوية وغير متساوية، وهذا واضح بتطبيق قوانين المجال المغناطيسي يعني حسب نظريتي. فالموضوع بسيط وسهل، هو أن الدبليو لديه شحنة، بالتالي السبين له يولد مجال مغناطيسي قوي جدا. الزي ليس لديها شحنة، لكن شحنتها تنشأ من اختلاف في الكتلة أو مركز الصيغة الكتلي، بحيث أنه يحصل انزياح خفيف جدا للكتلة في أثناء حركة وتكوين الكتلة، وبالتالي يظهر تيار ضعيف جدا. هذا التيار يعطينا مجال مغناطيسي أيضا أقل قوة كثيرا. طبعا الأنتي سيمتري يأتي من المجال المغناطيسي، لأنه مشتقات المجال المغناطيسي بالنسبة للمكان وبالنسبة للزمان، هذا ما يعطينا اختلاف الكتل. فيعطينا المجال المغناطيسي ضعيف جدا. هذا المجال المغناطيسي الضعيف جدا لديه أنتي سيمتري، أو أقصد لديه عدم سيمتري، عدم تناظر، لكنه ضعيف. وبالتالي عند تحلل الزي مباشرة يعطينا هذه الجسيمات القريبة جدا في كتلتها أو متساوية، اللي هو الميو نوت ميو سالب والميو موجب، بسبب عدم التناظر لكن ضعيف. في الدبليو بسبب أنه مشحون ولديه تيار، هذا التيار يعطينا مجال مغناطيسي. عدم التناظر في المجال المغناطيسي مباشرة يكسر الدبليو كسرا لا متجانسا، ويعطينا مباشرة كتلة ضخمة اللي هي الميون، وكتلة صغيرة جدا اللي هي النيوترينو. لكن في الزي الوضع يختلف بسبب عدم شحنته أو عدم ظهور شحنته كاملة، بينما تظهر بالشكل الضعيف جدا نتيجة كما يقال الدايبورز، تفاعلات الدايبورز، أو الإزاحات القليلة جدا للكتلة أو مركز الصغر الكتلة في أثناء السبين، وهذا الإزاحات ينتج عنها مجال مغناطيسي ضعيف. عموما احنا رأينا هذا الاشتقاق، طبعا اشتقاق جميل لكنه معقد جدا جدا، ويعني ربما هناك من يتابع هذا الاشتقاق بدقة، لكن من خلال هذا الاشتقاق وإدخاله في الباث انتجرال يمكننا أن نخرج الحدود المتعلقة بالكتل. وفي طبعا هو باث انتجرال، يمكن أن نعمل 2 باث انتجرال مضروبات في بعضها البعض. هذه ال 2 باث انتجرال، واحد للاجراج أو يعطينا الانتراكشنز، واحد يعطينا الكتل مباشرة. فالمتأكد من العلماء سيكونوا عرفوا هذه الطريقة، فإن شاء الله يتابعوها حتى يعني يعرفوا كيف يخلقوا الكتل، يتنبأوا بالكتل من خلال الباث انتجرال.
Just write down the formulas. Okay, so do you have, first of all, questions? Or so far so good? Okay. How many more examples do you want to see? Where's the joke? So, none, maybe. Okay. Here's the okay. So, then let me just write down what the third example is, but let us not calculate it. The third example would be QED plus gauge fixing. Where we have the Lagrangian density minus 1 over 4 f mu nu plus psi over 2 b square plus b times d mu a mu. And here you see, first of all, the normal QED Lagrangian, f mu, the kinetic term of the photon. And here you see now an auxiliary field, the so-called Nakanishi-Lautrup auxiliary field. It has a name, so let me write down the name. And this is exactly the form of this general case with the QB variables, and that is why I call them QB, because this is the standard name for such auxiliary fields in quantum field theory, and they appear exactly in the way the QB also has appeared before. Namely, b square appears with a constant coefficient, and b linearly appears multiplied with all the other fields, including time derivatives of other fields, and b dot does not appear. Therefore, b is clearly constrained. B dot doesn't exist. There is no canonical momentum for b. And if you work out the equation of motion for b, the equation of motion for b is simply psi times b plus d mu a mu equals 0. So you can eliminate b by, say, setting b equal to minus 1 over psi times d mu a mu. And so again, of course, this is constraint of second class, because the momentum of B and B itself are constrained, and so it's this typical pair of variable and momentum which is constrained. And so one can now eliminate B in the Lagrangian, then quantize, go to the Hamiltonian, go to the path integral, and so on. And let us not do this, but maybe let me just sketch it. Could eliminate B using equation of motion, then we would obtain L constraint without B. Then we would obtain the Hamiltonian density. We could canonically quantize. And that is what we did in quantum field theory 1b. And then we would have a correct path integral, which would contain the integral over a mu and over the canonical momenta pi mu, but it would not contain an integral over the Nakanishi-Lautrup field B. And by going through exactly the same steps as in the previous example, we could prove that the correct path integral is actually equal to the following, namely we integrate over a mu and we integrate also over b, and in the integrand we have the exponential of the original Lagrangian including the Nakanishi-Lautrup field. As simple as that. So again, here it is true that you can completely ignore the constraints, simply take the original Lagrangian, take all fields, integrate over all fields, but not about the canonical momenta, and that is the correct path integral for this theory. And if you now compare all three examples to this general case that I outlined in the beginning, then you see that all examples are of this form. So these QB variables, they appear always like this. So B square appears with a constant coefficient, B linearly times some combination of time derivatives and variables. In the previous case here, which was the most complicated of course, here also actually the A0 was the auxiliary field. A0 appeared in quadratic form with constant coefficient. A0 linearly appeared with some time derivative prefactors and so on. So all of the three examples were of the general form, and that is why in all three cases it works, and you can prove it also in generality. So these are all very important examples that one encounters in actual quantum field theory discussions, and therefore we now know that in all these important examples the path integral is the naive one that you get by ignoring all details and ignoring all difficulties and just writing down what you would immediately write down. That is true in an established form for all the relevant cases. And so having established this, we can now come to another topic for which we have hopefully enough time. Do you have any questions? It is motivated by trying to put the QED quantization onto a more general footing. There are very important and interesting useful generalizations of QED where the Nakanishi-Lautrup field helps a lot, and therefore including it in setting up the gauge fixing is very useful. At this point there are no advantages. For example, the theory is also Lorentz invariant if you eliminate the B, which is what we had. So there is no obvious disadvantage of the theory where B is eliminated, but we will in the next section of the lecture encounter cases where the B is actually advantageous, and then you will see. And then we will be able to come back to this case, and we will immediately know how one can quantize a theory involving such a B. But for QED alone, B or no B doesn't really matter. But it's nice to know that what is going on here. Okay, permanent chalk. That's a new discovery. Amazing. By the way, as an exercise, I did not prepare an exercise sheet for this week, so I don't know, maybe you want to have some nice Easter vacation or whatever. But if you have nothing else to do and you are interested in it, then I would very strongly recommend as an exercise for what we did today to go exactly through the Weinberg chapters that I mentioned. Go through exactly those discussions of exactly the same examples where he provides you with some details, and you will see that part of what he does corresponds to what we already did in quantum field theory 1. Then you can go through the corresponding calculations, and the other part of what he does corresponds to what we did today. So you can read this up once again and fill in all the details of calculations. Okay, new topic, hopefully sufficient time, on path integrals, namely path integrals for ground state expectation values and the appearance of the plus I epsilon prescription. So far, we have had path integrals for essentially position eigenstates, but we do not always want expectation values between position eigenstates, but very often, even more often, we want expectation values of the vacuum, of the ground state. And so how can we get from here to expectation values of the ground state? Let us do this on the generic level of quantum mechanics with quantum mechanics notation, not quantum field theory. And let's first work in the Hamiltonian framework without Lagrangian. And we assume that there exists a unique ground state, which is the state of lowest energy of the Hamiltonian, which I call capital omega. And without loss of generality, we assume that the eigenvalue is 0. Otherwise, we shift the Hamiltonian by a constant such that the eigenvalue becomes 0. Otherwise, we get lots of phases which are irrelevant. Okay? So we have one ground state which has 0 energy. And then the Hamiltonian might have other eigenstates which we might call En, where all the other Ens are bigger than 0. Then our Heisenberg picture state Q, T, which was the position eigenstate at time t, is of course given by e to the I h t times q at time 0. And let us now look at the following behavior. Let us look at the time t. What happens if we make the time t very, very negative, but we give the time also a small imaginary part. So t becomes minus capital T times 1 minus I times epsilon, where epsilon is a fixed positive number, but small. By the way, I always use two different notations for epsilon. So there is this epsilon and the other epsilon, and here I use this epsilon, which is called var epsilon in LaTeX. So I make this remark in every lecture. Okay, just to avoid confusion. You can call it whatever you like. But this is my epsilon for such small infinitesimal positive numbers. Let's look at the behavior if the time becomes very, very negative, but with a small positive imaginary part. Okay, so then we have the following: q, minus t times 1 minus I times epsilon. This state is now the following: e to the minus I Hamiltonian times t, and then e to the minus epsilon times t times the Hamiltonian acting on q at 0. So here we have the usual imaginary exponent, and here we now have a real exponent with a negative number e to the minus epsilon times t times the Hamiltonian acting on this state. So what happens if the capital T becomes very large and ultimately goes to infinity? So in order to see what happens is we insert a basis of Hamiltonian eigenstates. So this is a generalized sum or integral over all the energy eigenstates n. And let's do it like this. So we insert this basis here, n or En, I called it En, acting on q comma 0. Now if you imagine that I insert this here, what I wrote here, this is just a unit operator because it's a full basis. If we insert this unit operator at this position, then what happens is that the Hamiltonians act on the energy eigenstates and get replaced by the exponential of the eigenvalues. And then the exponential of the eigenvalues is just a number. I can write them here. So let's write them here. E to the minus I eigenvalue En times t, and e to the minus epsilon times t times En. And then I factored out to the left here the quantum state, and everything that stands here is a number. And what happens to those numbers? To those numbers happens the following. For the ground state, we have the energy is equal to 0. And so for the ground state here, therefore, this exponential is just 1 and stays 1 for all t. For all the other states, En is positive. Then this term here is an exponential damping, because here we have t goes to plus infinity, epsilon is fixed and positive, En is also fixed and positive, and therefore for all the other n, this is an exponential damping, and therefore all states go to 0 except the ground state, which just stays in the sum. Therefore, for t going to plus infinity, this projects out the ground state, let's call it omega, we called it omega, times the scalar product of this. So the ground state is projected out. And at this point, I want to refer you to quantum field theory 1 from 1920. There, this was discussed in section 2.4. We had an equivalent discussion in the operator formalism, where this is part of the so-called Gell-Mann-Low formula. And here it's part of the ground state discussion of the path integral. So anyway, we now know that you can get from a position eigenstate at very, very negative times with some imaginary part, you can go in the limit to the ground state. And so this is the connection between our original path integral with position eigenstates and path integrals for the ground state. So in order to make this transition, we have to use that trick of small imaginary parts and going to infinite times. Let's do the same for the opposite. So similarly, take the opposite, q comma plus t times 1 minus I epsilon. If so the left state, the time goes to plus infinity with a small negative imaginary part, the same thing happens, and it becomes, for t going to plus infinity, it becomes this scalar product times the ground state. And so therefore, the result is that in the limit, so it's, I think it's unfortunately hard to read, maybe I can write here. So in the limit t going to plus infinity of the following expression, qf evaluated at positive times 1 minus I epsilon, then any operators, then qi at time minus t times 1 minus I epsilon. This path integral with imaginary parts of the times, t goes to plus infinity, this gives a constant times the vacuum expectation value of the same operators. And this constant comes from these scalar products here, which are just some numbers which we don't know. But anyway, they don't depend on t in the limit, they are really constants. And so in this way we can project out the vacuum expectation value of whatever operators we want, just by only looking at position eigenstate expectation values but taking this particular limit. And interestingly, it doesn't matter which position eigenstate you choose, in the end, in the limit, the result always becomes the same, except the constant might depend on what position eigenstate you choose, but otherwise it's completely irrelevant. And so therefore, let me just write down what that means for the path integral. So I would maybe end the lecture with a path integral formula for the ground state, but we need some space, which is hard to get since we cannot clean. That's really weird. Friction? You mean like that? Probably. That's really stupid. I think it's not really much better. So I do not want you to leave without seeing the formula for the path integral, which gives you the ground state expectation value. So maybe let's use some colors. Maybe orange. Not orange. Green. There is also green, but I think green is kind of not useful. Okay, where were we? We know the path integral formula for this. So now up to the constant, we now know how to get the path integral for that. And so therefore, we have the following. So just as a guiding principle, in the path integral, oh, that looks nice. So the Hamiltonian would be replaced by itself times 1 minus I epsilon. So the Hamiltonian will now be multiplied with a small imaginary part, which you can interpret as the Hamiltonian minus I epsilon times something which is positive definite. Because the Hamiltonian is of course positive definite. So applied on any state, it gives something positive. And so this is the important thing here, which multiplies the plus I epsilon. Then in the path integral, we always had the integral over time. This is now replaced, of course, by an integral from minus infinity to plus infinity over time, and the endpoints are irrelevant. So the endpoints qi and qf, they are irrelevant as we just said. So let me then write down the formula for the Lagrangian. If the Lagrangian form is correct, then we can immediately write down the path integral formula for this, namely the vacuum expectation value of some time-ordered product of operators is up to a constant the path integral dq of t times all the operators times e to the I times the action. That's just it. And here the paths go up to infinity with arbitrary boundary conditions. Now the convergence of the integral, even though time goes to plus minus infinity, is of course guaranteed by the minus I epsilon. And so if you have time, let me assume that you have still 1 or 2 minutes more of time, then we can do a slight other nice form of the same thing. Namely, what is actually the constant? The constant can be obtained as follows. Namely, if you remove here the operators in between, then on the left-hand side you simply have the scalar product of the vacuum with itself. Vacuum is the norm of the vacuum state is 1. And then on the right-hand side you have the same constant times the path integral without the operators. So the constant can be divided out. It's just the norm of the vacuum divided by that other path integral without operators, and so therefore combining it, we can write it in the following way, which I now do, namely T01, let's forget about the arguments, it's always the same. This is now a ratio of two path integrals, namely in the denominator, let's start with there, we have the path integral of just the action with no operators, that gives this constant, and in the numerator we have the path integral of all the operators times e to the I times the action. And so this is of course a beautiful form for vacuum expectation values of arbitrary time-ordered products of operators. And that is very similar to the Gell-Mann-Low formula, which is a formula in the canonical formalism which we derived in that quantum field theory lecture in the operator formalism, where similar tricks are used. All right. We have now learned a lot of important building blocks for quantum field theory, and in particular those vacuum expectation values. They are extremely important objects in quantum field theory, probably the most important objects that one can calculate. And so here we now have a path integral representation for those vacuum expectation values of time-ordered products. This is the building block from which you can construct everything: observables, scattering, amplitudes, everything else. And so we now have the full general expression for it. Okay, having said that, thanks for your attention. Have a nice Easter, and then see you next week.
طبعا أنا أفكر في هذه المعادلة لأنها بطريقة ما ترتبط بنظريتي. حقيقة أنا حتى الآن لا أراها. نظرية تقول في الاكسبكتيشن فاليو بالنسبة للفاكيوم انرجي أن الفاكيوم انرجي تزيد مع الجاذبية. الفاكيوم انرجي تزيد مع الجاذبية، ليس فقط هذا، وإنما الفاكيوم انرجي سببها الجاذبية. طيب مثلا في نظرية تقول كالآتي: في الفضاء الخالي من الكتل فإن الفاكيوم انرجي تكون 10 أس ناقص 124، وهي التي تساوي مع الفرق بين النسبية العامة وبين الكوانتم ميكانيكس. 10 الفرق هي 10 أس 120. هذا هو الفرق أو النسبة. أنا جاءتني 10 أس 124، طبعا عندما تقلبها تأتيك 10 أس 123. يعني الفرق هو 10 أس 123، وهي قريبة من الفاكيوم، قريبة من الانرجي هيراركي، يعني بين النسبية العامة وبين الميكانيكا الكم اللي هي 10 أس 120. طيب هذا بالنسبة للفضاء الخالي من الكتل 10 أس 124. ما تعمله الكتل هي أن تزيد هذه النسبة، يعني مثلا من 124 تنقص من 10 أس سالب 124 تصبح 10 أس سالب 100، تصبح 10 أس سالب 50، تصبح 10 أس، وهكذا كلما زادت الكتلة مسببة للجاذبية، وبالتالي تنقص أو نقول تزيد هذه الطاقة من قريبة للصفر إلى أبعد قليلا من الصفر. طبعا 10 أس ناقص 124 هي قريبة جدا للصفر، تزيدها إلى أقل من أو أبعد من الصفر قليلا، لكنها أقل من الواحد. إذا وصلت الواحد مباشرة الفضاء صناعي الأبعاد سيدافع عن نفسه، ومباشرة الفضاء سيطرد الكتل أو يبددها، أو يجب أن لا تساوي الواحد. إذا جميع الفاكيوم انرجي مهما كانت الكتلة يجب أن تكون أقل من الواحد، لكن تختلف. في الثقوب السوداء هي قريبة من الواحد لكن لا تصل الواحد. في النجوم النيوترونية أقل من الواحد. على سطح الأرض يمكن حسابها بسهولة جدا في معادلة الطاقة، تعطينا 10 أس ناقص 45. وإذا حذفنا السي تربيع باعتبارها هي طاقة تعطينا 10 أس ناقص 29. هذه هي الطاقة الأرضية، هذه هي الفاكيوم انرجي بالنسبة للأرض، أو أنا أقول عليها الطاقة المطلوبة بالنسبة للأرض، الطاقة المطلوبة بالنسبة للأرض. طيب ماذا يحصل في الفاكيوم انرجي؟ معروف أنه تخلق جسيمات في الفاكيوم انرجي، يعني كلما زادت الفاكيوم انرجي كلما خلقت جسيمات. وهذا واضح أن الفضاء صناعي الأبعاد يخلق هذه الجسيمات محسوبا من الطاقة المسببة أو الكتلة المسببة وتطرد بعيدا. إذا الفاكيوم انرجي يخلق جسيمات منها، وهذا واضح في البير برودكشن. فيمكن حسابها على الأرض 10 أس ناقص 29 حولها إلى إلكترون فولت، يعني تبقى 10 أس ناقص 10. 10 أس ناقص 10 إلكترون فولت هي صغيرة جدا، لكن تكافئ ماذا؟ تكافئ حركة الجزيئات اللي هو في مدى الراديو ويف، حركة الجزيئات الغاز في مدى الراديو ويف، فتكافئ حركة جزيئات الغاز. وبالتالي نجد أن جزيئات الغاز ليست ثابتة على سطح الأرض، وإنما تتحرك بسبب هذه الفاكيوم انرجي التي تفعلها الجاذبية الأرضية. الشمس أكبر من ذلك، الشمس وصلت عندي إلى عدة إلكترون فولت، يعني هذه 10 أس ناقص الشمس 10 أس ناقص 30 أضربها بسرعة الضوء تربيع 30 أصبحت 18 لا 16 30 و 16 15 أو 14 10 أس ناقص 14. وعندما تحولها إلى هذه طبعا بالجول، عندما تحولها إلى إلكترون فولت تعطينا 10 أس 6 أو 10 أس 5 إلكترون فولت. هي رقم كبير جدا، هي طاقة الأرضية تسببها الجاذبية، وهي في مدى الميجا أو قريب من الميجا إلكترون فولت. وهذه تحفز طبعا التفاعلات النووية. طبعا الطاقة الأرضية لا تعبر عن الطاقة الكلية، لأن الطاقة الكلية هي الطاقة الأرضية زائد هاير سينرجي اللي هو الطاقات العليا الناتجة من ماذا؟ الناتجة من الهيتينج، الناتجة من تصادم الجزيئات، الناتجة من الضغط. هذه ما تسبب الانشطارات النووية والاندماجات النووية، وهذه ما تسبب طاقة. لكن أقل طاقة تساعد في الاندماجات النووية هي الفاكيوم انرجي أو الطاقة الناتجة من الجاذبية. أما بقية الطاقات هي عبارة عن ناتجة من احتكاك الجزيئات مع بعضها البعض، والتي تصل لقيم عالية جدا جدا. في قلب الشمس تصل إلى 20 مليون كلفن. طيب، فالفاكيوم انرجي هي خاصية أساسية للجاذبية، تزيد هذا الفاكيوم انرجي، الجاذبية تزيد هذا الفاكيوم انرجي. لهذا نجد أن الأوبريتور الذي يمثل هنا نقول لا أقول الجاذبية، لكن تمثل شيء له علاقة بالجاذبية، مثلا تمثل هاملتونيان الأعلى ربما هذا الأوبريتور، لأنه الكوميوتيشن بينه وبين الهاملتونيان يساوي زيرو، إذن هو يمكن أن نعبر عنه بالهاملتونيان الأعلى. في حالة الجاذبية وتعبر عن الهاملتونيان الناتج من الجاذبية. هذا الأوبريتور موجود في البسط. أما الموجود في المقام، الأكشن الموجود في المقام له علاقة بالطاقة المطلوبة، له علاقة بالطاقة المطلوبة، وهي على ما أعتقد 10⁻²² بالنسبة للفضاء المطلق. وبالتالي عند قسمة البسط على المقام يعطينا اللي هو الطاقة المطلوبة في الجاذبية التي شرحناها قبل قليل، لأن الأرض هو 10⁻⁵45 أو 10⁻⁻29 إذا حسبنا سرعة الضوء التربيع، أو إذا أضفنا سرعة الضوء التربيع 10⁻⁻29، والشمس 10⁻⁻14. فهذه بالقسمة، وهذا الاكسبكتيشن فاليو للطاقة بالنسبة للكواكب النجوم وما إلى ذلك تعتمد على الكتلة. المعادلة هي معادلة الطاقة، المعادلة التي تحسب هذا الأمر هي معادلة الطاقة. تعال نشوف. هذه المعادلة فقط بمقلوبها نقلبها. هذه المعادلة تعطينا إذا عوضنا الكتلة M capital و M small و R ب1 تعطينا 10⁻⁻123، وعند قلبها تعطينا 10⁻⁻124. وسنجد أن الكتلة M capital موجودة في البسط، وبالتالي M capital مرفوعة للأس الرابع، وبالتالي M capital تساعد على زيادة هذه الطاقة من الصفر أو قريب من الصفر، يعني 10⁻⁻124 تزيدها قليلا، لكن يجب أن لا تصل الواحد، لأنه إذا وصلت الواحد فإن الفضاء ثنائي الأبعاد مباشرة يدافع عن نفسه ويطرد الكتل، يخلق كتل ويطردها من التفاعل مباشرة، أو يطردها من الكوكب، أو يطردها من الM المسببة، من أجل إنقاذ هذه الكتلة العالية. فإذا خلق الجسيمات في الفاكيوم انرجي هو نتيجة للفضاء ثنائي الأبعاد للدفاع عن نفسه. بعد ذلك يكون تعامد الأرض لديها كتلة 10⁻⁴ ونصف قطرها 10⁻⁶. تعود في هذه المعادلة تعطيكم 10⁻⁴ انظر إلى MC سكوير، إذا جعلتوها يساوي 1 MC سكوير كلها أصبحت تساوي 1، فهذه تعطينا 10⁻⁻⁴ للطاقة الأرضية، وللشمس تعطينا 10⁻⁻14، الثوب الأسود تعطينا 10⁻⁵/6. انظر قريبة جدا من الواحد. بالتالي نجد أن الثوب الأسود الفضاء ثنائي الأبعاد يطور آلياته مباشرة. ال5 آليات المعروفة اللي هي زيادة الفضاء، تضخم الفضاء تحت الثوب الأسود وداخله، زيادة السبين، طرد الطاقة، طرد الكتل، موجات الجاذبية، كلها تفعل في الثوب الأسود إذا ابتلع نجم وزادت هذه الطاقة من 10⁻⁵ إلى 1 مباشرة سيفعل الفضاء هذه الآليات وينقص كتلة الثقب الأسود مرة أخرى. فهذا هو الاكسبكتيشن فاليو للنظرية مقارنة الفضاء الخالي من الكتل. فبعد ذلك يمكن تطبيق هذه الأفكار في هذا النتيجة التي في هذه النتيجة التي توصلنا إليها. هذه النتيجة التي توصلنا إليها، وبعد ذلك تكمل النتيجة إلى الواحد، لأن إذا أكملنا النتيجة هذه النتيجة إلى الواحد فإن الكتل تطرد مباشرة. طرد الكتل هذه يخبرنا مباشرة عن حجم الكتل وكمياتها وشكلها وحتى الإسبين وحتى كل ذلك من خلال هذه المعادلة. إذن أربط بين هذه المعادلة ومعادلة الطاقة التي شرحناها قبل قليل، ويمكنكم حساب الكتل والتنبؤ بها بإذن الله تعالى. السلام عليكم ورحمة الله.